Hello. So, today we are going to solve certain examples on multi-degree of freedom system. So, in the last lecture we have discussed about the various properties of mode shapes and natural frequencies, what is meant by orthogonality of mode shapes, what is meant by mass normalization, and today we are going to solve some numerical examples to show how to implement these concepts. So, let us start with this example. So, this is a 3 degree of freedom system. So, this is a 3 degree of freedom system with 3 masses. The first mass is m1, which is equal to m. Then there is a mass m2, which is also equals to m, and there is a mass m3, which is 2m. So, each of these masses are connected in the form given in the figure, and the spring constants for all the 3 springs shown is k. Now, let us, so as we can easily understand that this is a 3 degree of freedom system. So, the 3 degrees are the 3 translational motion of the 3 masses. So, let me call this as u1, which is my first degree of freedom. So, this is u1, then I have u2, which is the displacement of mass m2, and then finally, this is u3, which is the displacement of mass m3. So, u1, u2, u3 are the 3 degrees of freedom, and we are trying to find out the natural frequencies and the mass normalized mode shapes of the system. So, let me just reiterate. So, all this while we have been solving to obtain the natural frequencies and mode shapes of a 2 degree of freedom system. So, it is a good idea to see how to evaluate this natural frequencies and mode shape, mass normalized mode shape for a 3 degree of freedom system, so that extension to n degrees of freedom system or for any generic multi-degree of freedom system becomes easier. So, if we want to find out the natural frequencies and mode shapes of this system, the first thing that we have to do is find out the equation of motion. So, before we find out the equation of motion, we need to draw the free body diagram. So, let me draw the free body diagram of this system. So, if I draw the free body diagram, what I am going to see is the, let me first draw it for mass m3. So, this is mass m3, the degree of freedom is u3 or the displacement is u3. So, there is a inertial force which is m3 into u3 double dot, and then I will have k u3, and then I will have k u1 minus u3, and then k into u2 minus u3. Right. So, if I write down the force balance equation for mass m3, I will have m3 u3 double dot plus k into u3 minus k into u1 minus u3, and then minus k into u1 minus u3, and that is equal to 0. So, if I simplify this, I will have m3 u3 double dot plus minus k into u1 minus k into u2 and plus 3k into u3 equals to 0. This is my equation of motion 1. Okay. So, now we can go to the mass M2 and see what is going to be the free body diagram. So, if I draw the mass M2, what I will have is M2, which is having a degree of freedom U2, will of course experience an inertial force which is M2 into U2 double dot, and then I am going to have a spring force which is going to be K into U2 minus U3. So, if I write down the force balance equation, I will have M2 U2 double dot plus K into U2 minus K into U3, and that is equal to 0. So, this is my equation of motion 2. Similarly, if I write down the force balance for M1, I will have the degree of freedom U1 T and the inertial force and that is my equation 3. So, we have got the equation of motion for all the 3 degrees of freedom. So, as we have done earlier, we are now going to write them in a matrix form. So, let me write it in a matrix form. So, the equation of motion that I have is m1 u1 double dot plus k into u1 minus k into u3 is equal to 0. Then I have m2 into u2 double dot plus k into u2 minus k into u3 is equal to 0, and finally, I have m3 u3 double dot plus I have minus k into u1 minus k into u2 plus 3 k u3 is equal to 0. So, therefore, writing these equations in matrix form, we get the equation of motion in matrix form, and that can actually be written as m1 0 0 0 m2 0. Right. So, this is the equation of motion that I get. So, m1 is nothing but m. So, m1 is m, m2 is also m, m3 is 2m. So, let me write this as 2m. Now, unlike the previous example where we had a 2 degree of freedom system, here my mass and stiffness matrices are 3 cross 3. Since it is 3 cross 3, we will have 3 solutions for omega square from this equation, as well as the mode shapes will be 3 cross 1 vector or a vector with of length 3. One should also notice that even in this case, the stiffness matrix has turned out to be symmetric. The mass matrix here is diagonal. So, I mean the question of symmetry does not come into picture, but there could be cases, there could be systems where the mass matrix need not be diagonal. Even in those cases, if it is a linear system, the systems that we are dealing with in this course, the mass matrix will be symmetric and positive definite, okay, as well as the stiffness matrix. So, now let us try to solve for the natural frequencies first, and then we will move into mode shapes. So, to find out the natural frequencies, as we have done earlier, we have to equate the determinant of this matrix k minus omega square m equals to 0. This is what we have to equate it to. So, if I write it in expanded form, I will have this matrix as k minus m omega square 0, then minus k, then I have 0, then k minus m omega square and then minus k, then it is minus k, 3k minus 2m omega square, and determinant of that is equated to 0. So, if I try to solve this equation for finding out the solution for omega square, I get the equation as k minus m omega square into k minus. So, I am just writing the characteristic equation. And then I have minus k into so I have this as minus k square. So, I can, that is equal to 0. So, I can write take k minus m omega square common, and if I simplify, which I am not doing here to keep it simple, let me write this as it can be actually written as k square minus 5 m k omega square plus 2 m square omega 4 is equal to 0. So, this is the characteristic equation that we are going to get. So, if we solve this equation, the 3 roots that you get is omega square is k by m, and then omega square is 5 plus minus root over 17 by 4 k by m. So, these are the 3 roots that we get. So, let us find out the values of the natural frequencies from these 3 roots. So, the natural frequency that we get is root over k by m, and then we get this as 0.462 root over k by m, and the third frequency that we get is 1.510 root over k by m. So, these are the 3 roots that we get. Sorry, this is 4, 6, 8. So, therefore, we have to arrange these frequencies in increasing order. So, the first natural frequency omega 1 is the lowest of these 3 values, which is 0.468 into root over k by m. So, this is my first natural frequency. Omega 2, which is the next natural frequency, is k by m. So, this is the second natural frequency. And omega 3, which is the third highest value, which is 1.510 k by m, and that is the third natural frequency. So, these are the three natural frequencies that we get, and now the next job would be to find out the mode shapes of the systems corresponding to each of these natural frequencies. So, let us try to find that out. So, we have k minus m omega square, 0 minus k, then 0 k minus m omega square, and then minus k, 3k minus 2m omega square, A1, A2 and A3 is equal to 0. Therefore, from this expression, so the process is that if we have done that for a 2-degree of freedom system, if I just reiterate here, the process is to substitute the values of omega that we have solved earlier, and for each values of omega we need to find out the vector containing A1, A2 and A3, which is going to satisfy this solution, this equation. So, if I try to find this out, A1 by A2 is always going to be k by k minus m omega square. This is what we get from the first row of the equation. The next equation that we get is A2 by A3, sorry, this is A3, is going to be k by k minus m omega square. Okay. So, what we are going to do is we are going to substitute the value of omega into this two expression. This two expression has been derived from this equation, and then we are going to find out the numerical value of this, and that would be the ratio of A1 and A3 as well as the ratio of A2 and A3. So, by finding out these ratios, we can construct the mode shape, or we can obtain the mode shape for each of the natural frequency. So, let us first see what is when omega is equal to 0.468 root over k by m, which is my first mode shape, or mode shape corresponding to the first normal mode. So, if this is the case, then we see that A1 by A3 is going to be, if I plug in this value here. So, what I am going to do is just plug in this value here, and if I do so, then I will get A1 by A3 as 1 by 0.780. Okay. Similarly, A2 by A3 is also going to be, because the expressions are same, it is also going to be 1 by 7808. So, this is the two expressions or the two ratios. So, from these ratios we can see that our first mode shape corresponding to omega 1 equals to 0.468 root over k by m can be 1, 1 and 0.7808. Right. So, this could be our first mode shape that we have. Now, in order to find out the second mode shape, we have to do exactly the same thing, but in place of omega, we have to substitute omega 2, which is nothing but root over k by m. So, if we substitute this into this equation, then we get A1 by A3 as 1 by 0, which is undefined, and A2 by A3 is going to be again 1 by 0, which is also undefined. So, we can always assume A1 and A2 to be 1, but we cannot determine the value of A3. So, in order to find out the value of A3, let us try with the second expression. So, if it is k into A1 minus k into A2 plus 3k minus 2k into A3, that is equal to 0, then we can see that A3 equals to, so A2 by A3 is coming out to be 1 by 0. So, if I use A1 here, we can see that a possible solution of this is can be 1, 1 and it minus 1 and it is can be equal to 0. So, this is a possible solution of R2. Now, similarly, if we try to find out the third mode shape and simply plug in the value of omega 3 equals to 1.510 root over k by m into the above equation, we will see that R 3 is going to be 1 and then 1 and minus 1.2808. Okay. So, these are the three mode shapes that we have got corresponding to the system given. So, now if we try to find out the value of the mass normalized mode shapes, what do we need to do to find out the value of mass normalized mode shape? So, I know that R1 is equal to 1, 1 and 0.7808. So, in order to make it mass normalized, we have to first evaluate this product, which is 7808, into the mass matrix, which is M 0 0 0 M 0 0 0 2 M into 1 1 and 0.7808. Okay. This expression is nothing but R1 transpose into M into R1. This is the expression. So, if I evaluate this expression, this expression is going to be 1 1 and 0.7808 and that is going to be M into 2 into 0.7808, which is going to be 1.5616 M. So, if we find out this entire product, this is going to be 3.22 M. Therefore, my mass normalized first mode shape is going to be 1 by root over 3.22 M into 1 1 and 0.7808. This is the first mass normalized mode shape. So, if we try to find out the second mass normalized mode shape, so R2 is 1 minus 1 and 0. So, this is going to be the product has to be R2 transpose into M into R2, and that is going to be 1 minus 1 0 M 0 0 0 M 0 0 0 2 M into 1 minus 1 0. So, if we evaluate this, this is going to come as 2 M. Therefore, mass normalized second mode shape is going to be 1 by root over 2 m into 1 minus 1 and 0. So, this is our second mode shape mass normalized. So, similarly, R 3 mass normalized can be found out in similar way, and then R 3 mass normalized come out to be 1 by root over 5.28 m into 1, 1 and minus 1.2808. So, this is going to be the third mass normalized mode shape. So, now once we have got all the mass normalized mode shape, we can write down the mass normalized modal mass normalized modal matrix. So, which is phi mass normalized. So, each column of this modal matrix, which is going to be 3 cross 3, are the mass normalized mode shapes. So, this is R 1 m n, then we will have R 2 m n, and then we are going to have R 3 m n. So, if I write this out in a expanded form, I will have 1 by root over 3.22 m, then 1 by root over 3.22 m, and then I will have 0.7808 by root over 3.22 m. Similarly, I will have 1 by root over 2 m, I will have minus 1 by root over 2 m, and then I will have 0, and similarly 1 by root over 5.28 m and 1 by root over 5.28 m, and then minus 1.2808 root over 5.28 m. So, if I can simplify this, I can write this as 1 by root over m and then 0.557, 0.557 and 0.435. Similarly, 0.707, 0.707 and 0, and 0.435, 0.435 and then minus 0.557. So, this is going to be the expression for the mass normalized mode shape. We can check that this mass normalized mode shape into, so phi m n into m into transpose of this into phi m n has to become a identity matrix of 3 cross 3. So, with this we are going to end this lecture. In the next lecture we will solve another problem to find out the response of a freely vibrating multi-degree of freedom system. Thank you.